So today we're going to be covering the column that is numbers 71 through 87. So without further ado, let's go ahead and get started at 71. Okay, so we have an angle in standard position that has a degree of negative 220 degrees. What quadrant does the terminal side lie? So what this question is asking is that we have an angle, which we know is based off of, when we look at the Cartesian plane, negative 220 degrees moves in an anti-clockwise direction. This will hit 90 degrees, 180 degrees, and then up here will be 270 degrees. So that means that my angle will end somewhere in this direction. We're asking which quadrant does the terminal side lie? Well, we know the quadrants are numbered 1, 2, 3, and 4. So that will be ending in quadrant 2. Boom. So we got an answer of quadrant 2. If we look at number 72, we're dealing with a slightly different style problem. We're converting 210 degrees into radians. We remember that degrees and radians are two different types of degrees of rotation or measures of rotation. So let's take 72 and we want to convert 210 degrees into radians. Okay? Well, we know that this is going to be set up using the proportion of, let's say, the number of degrees over 180 is equal to the number of radians over pi, because 180 degrees is equal to pi radians. And I just plug in what I know and solve for what I don't. In this case, I know the number of degrees, so I'm going to place 210 degrees in right here. What I don't know is the number of radians. So I'm going to say the number of radians is x. And my whole process right here is going to be solving for x. In this case, I notice that this can be reduced, but before I even reduce that, I'm going to go ahead and move that pi over here by multiplying by pi. So I'll get 210 pi over 180 is equal to x. Now my job is just to reduce 210 over 80. I know that 210 over 180 will reduce down to 21 over 18. The 21 over 18, these are both divisible by 3. I'll get 7 over 6 pi, or 7 pi over 6. They're both the same thing depending on the format of your answer. So there we go, 210 degrees into radians. Number 73, very similar style problem. I'm going to convert negative 160 degrees into radians. So negative 160. Okay. So I'm going to set up the same proportion that I did before. I know that in a circle, 180 degrees is equal to pi radians. So I'm going to fill in the unknown and the known. So in this case, I have negative 160. I know the number of degrees. So 180 equals some unknown radian measure. But I do know that is negative 160. Awesome. Okay. So what I'm going to do is I'm going to multiply both sides by pi. So that is a negative 160 pi over 180 is equal to x. And then I'm just going to go ahead and start simplifying this however I can. So first off, I know that can reduce down to negative 16 over 18. These are both divisible by 2. So it looks like I get negative 8 over 9. So it could be that. Or if you wanted the pi off to the side, it would be negative 8/9 pi radians. Again, same answer, different format. That's number 73. Let's take a look at number 74. Number 74, we are converting the other direction. I have negative 13 pi over 15 into degrees. So negative 13 pi over 15 into degrees. So like the last problem, I know the ratio between the two. I'm just going to fill in what I know and what I don't. So I know the number of degrees over 180 is equal to the number of radians over pi. In this case, I know the number of radians. So I'm going to call my degree x equals, in this case, it is negative 13 pi over 15 over pi. Okay. So now with this is a complex fraction. The way that I'm going to solve this is I'm going to keep the top fraction, change division multiplication, and flip it. So I know this is really the equivalent of x over 180 is equal to negative 13 pi over 15, kept, changed, flipped. Okay. What that will allow me to do is it allows me to cancel out, in this case, I cancel out the pi. So I just have negative 13/15. So I have x over 180 is equal to negative 13/15. If I wanted to solve this, I'd multiply both sides by 180. So x equals negative 13 times 180 over 15. Okay. Now I'm going to reduce this as much as possible. Now I could multiply 13 times 180 and then reduce, but what I notice is that 180 and 15 are reducible. So 180 and 15 are both divisible by 3. Actually, they're both divisible by 5, so let's do 5 first. So negative 13. 180 divided by 5 is going to be, let's see, it's going to be 3 with 3 left over, 36. That divided by 5 is 3. If I reduce the 36 and the 3 by 3, I'll get negative 13 times 12 over 1. So I'm just left with negative 13 times 12, which is going to give me, let's see, 144 plus another 12, negative 156 degrees. Awesome. So I have negative 156 degrees. Perfect. So that was number 74. Let's take a quick look at number 75. Okay. Number 75 says convert 3 pi over 2 to degrees. This one actually looks a little easier. So 3 pi over 2, we want to convert that into degrees. So I'm going to fill out my same general formula. Degrees over 180 is equal to some unknown number of radians over pi. So x over 180 is equal to 3 pi over 2 over pi. In order to solve this, I need to keep change flip. In order to flip that, I need that to have a denominator as well. So x over 180 is equal to 3 pi over 2, kept, changed, flipped. Then what that allows me is I can cancel out these pi's. And I just have x over 180 is equal to 3 over 2. Then to isolate x, I'm going to multiply by 180. So x equals 3 times 180 over 2. I notice 180 over 2 does reduce. So 3 times 90 over 1, which is just going to be 270 degrees. Perfect. So that was number 75. Okay. Now let's take a look at number 76. We're into a different style question. For 76 through 83, so for this blurb right here, we're going to evaluate and give answers in exact form, no decimals. So one of the big things, if I try and evaluate the sine of 120 degrees, I can get an answer in my calculator super quick, because as of right now, let's make sure my calculator is in degrees, so I'm good. If I type in 120 and then hit sine, I'll get this big long decimal place. That's not what it's asking for. Yes, that's almost the right answer, but it's not what it's asking for. In fact, if I try and use a more advanced calculator, I run into the same problem. So if I say, okay, first off with this one, I need to first check my mode. So I go to mode, and I'm in radians, so I'm going to move over to degrees. Now I can enter in degrees. So I can quit. So if I type sine of 120 degrees, I get that same big huge decimal. So what does it mean, no decimals? Well, what we're going for right here on number 76 is the sine of 120 degrees is evaluated out on the unit circle. So the unit circle gives me something like this. And 120 degrees is going to give me that angle right there. Well, I know this is 90 degrees, and this is 30 degrees, which will give me my 120, which means that I have created a triangle right here with 60 degrees. This is a 30, 60, 90 triangle. which is one of our special right triangles. A 30, 60, 90 triangle. If I redraw it right here, let's say that's 60, 30, and 90, is going to give me a 1, 2 square root of 3. That's the special right triangle relationship. However, I know that this has a radius length of 1. So in order to get that translated over, I know I just need to divide this entire triangle in half. So now what I have, it's still a 30, 60, 90 triangle, except for in this case, it's going to be a 1 square root of 3 over 2 and a 1/2. Everything has been divided in half. And I want to find the sine. Well, if my original angle is right here, I want to find the sine. That is going to be opposite over hypotenuse. Why opposite over hypotenuse? Because of SOHCAHTOA. So opposite over hypotenuse is going to be square root of 3 over 2 over 1, or just the square root of 3 over 2, and that's what it's looking for. Give me the sine of 120 degrees without rounding, square root of 3 over 2. Let's double check and make sure that is our previous answer. So square root of 3 over 2 should give me that. So let's check this out. Square root of 3 divided by 2. Yep, there we go. Okay. So that was number 76. Let's take a look at number 77. It should be a very similar style problem. Okay, so I have the cosine of pi over 2. Okay, so if I have the cosine of pi over 2, I'm going to set up that same scenario. Okay, and additionally, we know cosine from SOHCAHTOA is going to be the adjacent over the hypotenuse. This is what we're looking for right here, is the adjacent over the hypotenuse. Okay, well, what is pi over 2? Well, that is a number of radians, and if I know that this is pi radians, pi over 2 is going to be directly right here. So I don't actually have an angle to do. What I do know is that this is of length 1, okay? Well, if my triangle looks like this, it's not really a triangle anymore, is it? The COHCAHTOA, or the Ka part, adjacent over hypotenuse, doesn't necessarily make sense. But if I switch it over to its unicircle equivalent of circexor, tix, SYR, CXR, TYX, cosine is just the x value divided by the radius. Well, what is the x value at this point? Well, the x value is going to be 0, the radius is going to be 1, and the y value is going to be 1. So it's 0 over 1, or 0. Perfect. So that's number 77. Let's take a look at number 78. Okay. Number 78 is the cosine of 135 degrees. Okay. So the cosine of 135 degrees, I'm going to do the exact same thing as we did before, set up the unit circle. So I draw my axis. And I know this time I'm dealing with a positive. Let's see, this is 90. This is 180, so it must be somewhere in here. And if this is 90 to get to 135, this is 45. Ooh. And so that means the triangle that I have created has 45 degrees left. So this must be that other type of special right. 45 degrees left, 45 degrees, 90. Okay? And now this special right triangle is going to be 1, 1 square root of 2. We also know that the radius of our unit circle is always going to be 1. So how do I get 1 to be the square root of 2? Well, I'm going to multiply everything times the square root of 2. Let's see, if I multiply that times the square root of 2. Sorry, backwards. I'm going to divide all of these by the square root of 2. I was looking at it from the original unit circle here. I got to go backwards. So to get from here to here, I'm going to divide everything by the square root of 2, which means my triangle is still a 45, 45, 90. But this is going to be a 1 over root 2, and a 1 over root 2. Now I know this is not rationalized, but it's going to get us to where we want to go. Okay. So we know we can either look at SOHCAHTOA or the unit circle equivalent of Sir Kexer Tix. And we're looking at the cosine of 135 degrees. The cosine is going to be either the x over the radius or the adjacent over the hypotenuse, however we want to look at that. The x value is going to be right here. And in this case, my x value, let's not forget about the fact that my x value is a negative number because it's going in the leftward direction. I might get caught up if I'm just looking at the adjacent because I would think that is a positive value. It's a negative 1 over root 2 over the radius, which is 1. So this is just going to be the negative 1 over root 2. And at this point, if there's an answer that looks like this, select it. Otherwise, we know the rationalized version, which is probably going to be what you're seeing, is going to be negative root 2 over 2. And the way we get to negative root 2 over 2 is I multiply top and bottom by a square root of 2 in order to rationalize it. There we go. So that was number 78. Let's take a look at number 79. Okay. 79, we're doing the same thing, except for I've got radians again. So I'm looking at the sine of 11 pi over 6. I don't know why that was so difficult to write. 11 pi over 6. Okay, so when I draw my unit circle, I know that a full circle is 2 pi, or this would be 12 pi over 6, which is 2 pi. I know I'm just shy of that. So I'm going to be right here, which is 11 pi over 6. So I know that the only remaining piece right here is going to be a pi over 6. Now, if you remember your pi over 6s, that's awesome. Most of us are going to know pi over 6, and I'm going to have to convert this. Well, if I know pi is equal to 180, pi over 6 is 180 divided by 6, which is roughly 30 degrees. So I know this is going to be a negative 30 degrees, which makes that a 30, 60, 90 triangle, or a 1, 2 square root of 3. In this case, a negative 1, because again, we're going down on the y-axis. Okay. Well, if this has a radius always of 1, how do I get this, which has a radius of 2, down to a radius of 1? Well, I divide everything on this by 2, and that will give me my actual triangle of which we're going to use. Okay. So this is 1, negative 1/2, and root 3 over 2. Okay. So I'm going to use this triangle right here, and we know that it's either SOHCAHTOA or Sir Kexer Tix. Okay. I'm looking for the sine. So the sine, I'm either looking for the y value over the radius or the opposite over the hypotenuse, whichever one. Opposite is this, which is my y value, over the radius, which in this case is going to be 1, or the hypotenuse, which is also still just going to be 1. So negative 1/2. There we go. So that is number 79. Let's take a quick look at number 80. Number 80, we have the cosine of negative 315 degrees. More of the same. I'm going to draw my unit circle. Negative, I know I'm heading in this direction because I'm going anti-clockwise. Let's see, that'd be 90, 180, 270, 360, somewhere in this region. I know if this is 270 and this is 360, well, let's see, I am 45 degrees past, which means that my triangle that I'm going to use has 45 degrees left in it. So I'm going to take that information and say, hey, dealing with a 45, 45, 90 triangle, which should be 1, 1, root 2. But how do I get from a root 2 to a known radius of 1, well, I'm going to divide everything by root 2. So that means this is divided by root 2. This is divided by root 2. And this is divided by root 2. This is the triangle I'm using. And remember, I'm always dealing with that edge right there. So I have so ka toa, or the unit circle of sur kexer tix. Okay. I'm dealing with cosine. So cosine is either the x value divided by the radius or the adjacent over the hypotenuse. It doesn't matter, you're using these two numbers. So I get 1 over root 2 over a 1, which I know is 1 over root 2. This is the unrationalized answer, which you may get, but the more likely answer is going to be the rationalized version, which is going to end up being root 2 over 2. And I kind of glanced over this previously. How do I get to that value? Well, I know that 1 over root 2, I cannot have a radical in the bottom. So if I multiply it by another root 2 over root 2, square root times square root is going to give me a 2. 1 times square root of 2 is going to leave me with that in the top. That is how I get from that to that. Okay, so that was number 80. Let's take a quick look at 81. Okay. So 81, I'm finding the cosine of 3 pi. Okay. So it looks like I'm dealing in radians right now. Okay. So what I know is that I'm heading in a positive direction, which means I'm heading anti-clockwise. I think I said anti-clockwise before on this one, but that's actually clockwise. So I'm heading anti-clockwise right here, 3 pi. So I know I get pi, and then as I come around, 2 pi, and then I keep going on the circle until I hit this again, which makes that 3 pi. So 1, 2, 3, 4, 5, 6, 7. I just keep counting my way up. So I'm all the way over here. Okay? Well, that doesn't really make a triangle. In fact, it just makes a line. I know that line is of length 1. So a couple things that I can pull from this. Well, I know that the radius is going to be 1 because the radius is always 1. I also know because this triangle has no height, my y value is going to be 0, but my x value does exist, and my x value is 1 unit in the leftward direction, so -1. So even though it's just a line, I have some information to use. And I can use either so ka toa or sur kexer tix. In this case, I'm looking for the cosine, which is going to be the x value over the r. So -1 over 1, which is -1. Perfect. So that was number 81. Let's take a quick look at number 82. Very poorly written 82 with that. There we go. So I'm looking at the sine of -180 degrees. Okay. So with -180 degrees, I draw my unit circle. I'm going in the negative direction, which means I am going clockwise, all the way up to 180 degrees. So I'm over here again. So just like this 3 pi, I ended up over here, -180 degrees, I'm over there again. So I've got my line going to the left of length 1. Doesn't look like much, but I do know a few values. My radius is 1, my y doesn't exist, and my x is -1. So ka toa or sur kexer tix. Okay. I'm looking for sine. Sine is either the opposite over the hypotenuse, which can't really tell much going on right here, but I do know it's the y over the r, in which case this is going to leave me with a 0 over a 1, or just 0. Perfect. That was 82. And the last one of this type is number 83. Let's take a look at what that one would be like. Okay. So number 83, there we go, is the sine of 7 pi over 2. Okay. So if I wanted to rewrite this in a more helpful format, I might rewrite 7 pi over 2 as a mixed number. And I know 7 pi over 2 is going to be 3 pi's plus pi over 2. Because 3 pi's is 6 over 2. And that'll help me a little bit when I'm drawing it, because what I know is that I'm moving in an anti-clockwise direction for a positive value. I know that this is going to give me pi, and as I keep going, every half circle is pi. So 1 pi, 2 pi, 3 pi, and then this would be 4 pi. So I'm going to be somewhere between 3 pi and 4 pi. If I add a pi over 2, I'm going to end up straight down here. So 3 1/2 pi, or 7 pi over 2, straight down here. And just like the two previous ones, I don't really have much of a triangle, but I do know its length is 1. So my radius is still of length 1. My x value this time doesn't exist, but my y value is -1 because it is going straight down. So I can either use so, ka, toa, or sir, kexer, tix. Looking for the sine, which means I'm looking for the y value over the radius, in which case is -1 over 1, which is -1. Awesome. So that's the end of that style of question, but we still got 4 more to go. So these are real quick. Let's look at number 84. Okay. So for questions 84 through 87 on the unit circle, in what quadrant does this exist? Okay. And so what's going on here is we have to look at those general relationships. We know that the unit circle is comprised of this. And I know in all 4 quadrants, I'm looking at either sir, kexer, tix. I know the sine is y over the r value. So I'm going to look at the signs of my x's and my y's and see what's up. Okay. Well, in this case, I have a positive x and a positive y. In this case, my y is positive, my x is negative. Down here, they're both negative, -x, -y. Here, my x is positive, but my y is negative. So when I ask myself, when is cosine negative? Cosine is the x value over the r. Seeing as r is always positive, when is my x going to be negative? Well, that's going to be here and here. Negative divided by my always positive. R is always positive, so when is it negative? During these two things. So quadrant 1, 2, 3, 4. That'd be quadrant 2 and 3. Awesome. That's 84. 85 is a very similar style problem, but it's when is cosine positive. So if you like this method, we know that cosine is positive on these two quadrants because a positive divided by the always positive radius will yield a positive, so 1 and 4. Or a different way to look at it is you could remember the mnemonic device of all students take calculus. In this quadrant, all the functions, sine, cosine, and tangent, are all positive. In this one, the students, only the sine is positive. The cosine and the tangent are negative. Take. So the tangent is positive, but the sine and the cosine are both negative. Calculus, the cosine is positive, but the sine and the tangent are both negative. Cool. So it's a different way of reading it. All students take calculus in quadrant 1, 2, 3, 4. So if I'm asking myself, when is the cosine of theta positive? The cosine is positive here and here, which is exactly what we saw here and here. So quadrant 1 and 4. Okay. That was 85. Let's take a look at 86. When is the sign negative? In this case, we're just going to go immediately to the device that we know. We know all students take calculus. When is sine negative? Well, I know sine is positive here and here, which means it's going to be negative on these two bottom quadrants. So 1, 2, quadrant 3, and quadrant 4. Boom. That was 86. 87, we're going to use that same device. When is the sign positive? So all students take calculus. Well, in this case, I know the sign is positive both here and here. So quadrant 1 and 2. Boom. Okay, and there we go.